One of the most interesting applications of trigonometry is analyzing bearing in air or marine navigation. In this section, we'll see how the law of sine can be useful in both navigation and surveying. So what exactly is bearing? The bearing of a ray is the measure of an angle describing its direction. Depending on the setting, this can be done in several different ways. In air navigation, bearing is given as a non-negative angle less than 360 degrees measured in a clockwise direction from due north. So all semester we've been analyzing positive angles as being counterclockwise measured from the positive x-axis. However, in air navigation, angles are measured from a ray pointing due north. We can model that as the positive y-axis. Then we're going to rotate in the clockwise direction to get a positive rotation. A ray with a bearing of 60 degrees would be indicating the northeast direction. A ray with a bearing of 150 degrees would be indicating a southeast direction. A ray with a bearing of 225 degrees would have a southwest direction. In solving any type of navigation problem, it's important to note the coordinate system and the method by which angles are defined. Different from air navigation, marine navigation and surveying defines bearing a little differently. The bearing of the ray is an acute angle that the ray makes with a ray pointing either due north or south. Thus, marine navigation and surveying deal with angles less than 90 degrees. For example, a ray with a bearing of north 40 degrees east begins with a ray pointing due north and then measures 40 degrees in the direction of east. On the other hand, a ray with a bearing of south 27 degrees east is measured from due south, or the negative y-axis, in the direction of east. So the first cardinal direction anchors the initial side of the angle, and the second cardinal direction indicates the direction in which the terminal side will be rotated. Another example, a ray with a bearing of north 60 degrees west is measured from due north in the direction to the west. And finally, a ray with a bearing of south 15 degrees west is measured from due south 15 degrees to the west. This means that in marine navigation and surveying, the angles are not only always acute, that is less than 90 degrees, they are always positive. Yet a positive angle can be rotated in either the clockwise or counterclockwise direction. And once again, in air navigation, all bearings are measured from a ray pointing due north in the clockwise direction, and they can have values between 0 and 360 degrees. Let's take a look at an example that uses both types of bearing. In example 7, we will examine air navigation. During an important NATO exercise, an F-14 Tomcat left the carrier Nimitz on a course with a bearing of 34 degrees and flew 400 miles. Now, as we go through the information in this problem, let's map out a diagram representing the path of this F-14. Since this is air navigation, all bearing will be measured from a ray pointing due north. Thus, a bearing of 34 degrees points out into quadrant 1. Notice the 34 degrees is measured with the positive y-axis, not the usual positive x-axis. The length of this leg of the trip is given to be 400 miles. Then, the F-14 flew for some distance on a course with a bearing of 162 degrees. To model the change in the direction of this F-14, I'm going to draw another compass rose, again measuring all bearing from due north. This time the bearing is 162 degrees. If we rotate from due north 162 degrees, that's going to put us somewhere in quadrant 2. So measured from due north, this is the angle 162 degrees. Now, we don't know the distance, so we'll just call this distance x. Finally, the plane flew back to its starting point on a course with a bearing of 308 degrees. So once again, I'm going to construct a compass rose here indicating due north. The F-14 goes back to its original location with a bearing of 308 degrees. Again, that 308 is measured from the positive y-axis to the terminal side of the ray in the clockwise direction. We don't know the distance of the final leg of the journey, so we can go ahead and call that y. Our problem is to figure out this final distance that we have labeled y. The simple law of sines will certainly offer us some assistance, but we need to know the interior angles of the triangle. At the vertex at the top, we can easily determine this angle, recognizing that that angle and the 162 degree angle make a straight angle or a 180 degree angle. So we can calculate this angle by subtracting 162 from 180 to get 18 degrees. But do recognize that's only a portion of the interior angle of the triangle, of the angle at the top vertex there. To find this portion of the angle, we can recognize that with the two north-south rays, we have a pair of parallel lines. These parallel lines are cut by a blue transverse line here. From geometry, recall that alternate interior angles are equal. So because we're given the measure of 34 degrees at the angle on the bottom, we can also determine that this angle is 34 degrees. Thus, this interior angle of the triangle is the sum of 34 and 18, and that's going to give us 52 degrees. This angle will certainly be helpful in the law of sines. If we take sine of 52 degrees divided by y, we'll be able to set that equal to another ratio on the triangle and solve for y. Because we know that this distance is 400 miles, it would be helpful to determine this angle right here. Once again, recognizing that the north-south rays form a pair of parallel lines, and they're cut by a green transversal line, and we know that alternate interior angles are equal, this angle is therefore equal to this little angle right here. Notice that the angle we're attempting to calculate completes a 360 degree rotation when added to the 18 degrees and the 308 degrees. So by taking 360 degrees and subtracting 18 degrees and subtracting 308 degrees, we can calculate this angle to be 34 degrees. Now that we know two interior angles of the triangle and at least one opposing side, we can solve for the distance representing the final leg of the plane's flight using the law of sine. That is, sine of 34 degrees divided by its opposing side, 400, will be equal to sine of 52 degrees divided by its opposing side, which we've labeled y. Solving for y, we obtain 400 times sine of 52 degrees divided by sine of 34 degrees. Be sure that your calculator is in radian mode and degree mode. We will be in degree mode for the majority of this chapter. So we have 400 sine of 52 divided by sine of 34, and this gives us to the nearest tenth 563.7 miles. 563.7 miles. So in order to solve for that final distance, we simply needed the bearing at each point, at each turn for the F-14 Tomcat, and the measure of one side of that triangle. Remember, for air navigation, bearing is always measured from a ray pointing due north, measured in the clockwise direction to the terminal side of the angle. For marine navigation and surveying, it's a little bit different. Let's try example 8 as a surveying problem. A surveyor located the corners of a triangular piece of property, started at one corner, and walked 480 feet in the direction north 36 degrees west to reach the next corner. So the surveyor is going to begin in the northwest direction. So I'm going to identify a ray pointing due north and recognize that rotating to the left would be the west direction. Notice the angle 36 degrees is a positive angle, but I'm rotating in the counterclockwise direction from due north. So the angle being described here is this 36-degree angle, and that distance is 480 feet. The surveyor then turns and walks south 21 degrees west. So at this vertex, once again, I'm going to draw a little compass rose to guide my diagram here. Because south is the first cardinal direction given, we're going to measure this ray from due south to the west. And we're going to go 21 degrees to the west. So this angle right here is our 21-degree bearing. The length of that segment of the property is not given. I'll just label it X. Finally, the surveyor walks in the direction north 82 degrees east. So once again, at this corner, we'll construct a little compass rose, northeast. You can think of that north 82 degrees to the east or 82 degrees east of north. So we are measuring this angle as 82 degrees. The length of this segment is not given, so we'll just label it Y. The surveyor needs to determine from these measurements the perimeter of this piece of triangular property to the nearest foot. In order to do that, we need to know the measures of the interior angles, and then we can apply the law of sines to solve the triangle. Let's begin with the vertex at the top. Notice that because this north and south ray is parallel to this north and south ray, and those two parallel lines are cut by the blue transversal, and alternate interior angles are equal, then this 36-degree angle is equivalent to this 36-degree angle. Adding those two angles together, we get the interior angle of the triangle of 57 degrees. Once again, using the principle of alternate interior angles, recognizing that our north-south rays are always positive, the 21-degree angle up here is equal to a 21-degree angle right here. Now, if from that ray pointing due north to the green terminal side is 82 degrees and 21 degrees is represented here, that's going to leave behind 82 minus 21, or 61 degrees for this angle. Now we know that the sum of the angles in a triangle is 180 degrees. So if we subtract 57 and 61 from 180 degrees, that's going to give us this remaining angle of 62 degrees. Because we know one angle and its opposing side, we can use the law of sines to determine this side we've labeled Y. We can express this as sine of 61 degrees divided by 480 is equal to sine of 57 degrees divided by Y. We can solve for Y by cross-multiplying and isolating Y to obtain 480 sine of 57 degrees divided by sine of 61 degrees. We can approximate this to at least the nearest tenth. We need to round our final answer to the nearest foot, so we'll take this one a decimal place more in order to keep our calculation a little more accurate. Looks like we get 460.3 for the length Y. And that's in feet. Now, once again, we can use this ratio and set that equal to sine of 62 over its opposing side in order to calculate X. That is sine of 61 degrees divided by 480 is equal to sine of 62 degrees divided by its opposing side X. Isolating X, we get 480 sine of 62 degrees divided by sine of 61 degrees. Notice this calculation is very similar to the previous one. It's different by one angle. So To be quick and efficient, I'm just going to type second entry. That's going to recall everything that I just typed in. And then I'm going to use my arrow keys to change that one angle from 57 to 62. And our next calculation is 484.6. So X is approximately 484.6 feet. We can then determine the perimeter of the piece of property by summing the sides. We have 480 plus 484.6 feet plus 460.3 feet, and to the nearest foot we get 1425. The perimeter then is approximately 1,425 feet. So once again, there's two types of bearing. A bearing measured from due north in the clockwise direction between 0 and 360 degrees is generally used with air navigation. A bearing for marine navigation or surveying is measured from a ray pointing either due north or due south in the direction of east or west, and that's always measured by an acute angle or an angle less than 90 degrees. From these applications, you can certainly see that the law of sines simplifies our problems and is a very useful way for analyzing navigation and surveying.